let's get started with our third and final part. So in the first two parts so far, we have we finally learned what a Dirichlet process is and what a Chinese restaurant process is. And so in this part, we're going to really be building our way up to inference. And then finally seeing some other, also, a wider tour of Bayesian nonparametrics at the end. Okay, so recall we have this idea of a Chinese restaurant process. Each customer walks into the restaurant. They sit at an existing table, a table that somebody else is already at, with probability in proportion to the number of people who are there. And they form a new table. They sit at a new table with probability proportional to alpha. And we saw that the marginal for the categorical likelihood, the GEM prior, is exactly the Chinese restaurant process. And so now we see this idea that the Chinese restaurant process and the Dirichlet process are the same in some sense, but different in that one describes sort of both the proportions of the clusters and the cluster assignments, whereas the Chinese restaurant process describes just the cluster assignments. Actually, I'll just briefly mention, by the way, I believe the story about why this is called the Chinese restaurant process, and this might be apocryphal, but I think it's true, is that apparently Jim Pittman and Dave Aldis were thinking, I noticed that in the San Francisco Bay Area that Chinese restaurants have this ability to always accommodate more people. In particular, no matter how many people are already sitting at a table, we can always fit a few more, and no matter how full the restaurant is, we can always find a new table and fit some people there. Hence the name Chinese restaurant process. Okay, so I want to make a little bit of a note here that the ordering of the tables here really doesn't matter. In fact, there's sort of nothing to that. There's no content to that. I mean, after all, these are clusters, and when we examine clusters, there's no ordering on the clusters. There's just a bunch of points that are all together here, a bunch of points that are all together here, and a bunch of points that are all together here. And so here we may have happened to have chosen that Z1, Z2, Z7, and Z8 are all at table 1. 3, 5, and 6 are all at table 2, and 4 is at table 3, but somehow we could have named the table as anything else we wanted, and this would still express the same clustering of the data points. And so a way that we can make that formal is we can say that the thing that's really going on here, the thing that we really care about, is the partition of the data points of 1 through n. And so that's what this capital pi is standing for. It's saying what is the partition of the data points 1 through n. And the set notation is just saying that 1, 2, 7, and 8 sit at a table together. The order at that table doesn't matter. They're just all at a table together. 3, 5, and 6 sit at a table together. 4 sits at a table on its own. And because it's all in a big set, the order of the tables themselves don't matter. And so again, we call this a partition of bracket 8. And bracket 8 is just notation for the integers 1 through 8. And it's a set of mutually exclusive and exhaustive sets. That's the idea of clustering, that every data point belongs to one and only one group. It's clustering. Okay, so now what we can do is we can ask ourselves, well, what is the probability of this seeing? Well, the first person who walks into the restaurant, that's easy. They sit at any new table with probability in proportional to alpha, and any old table with probability in proportion to the number of people who are there. Well, there's only one option for them. There are no tables yet. They have to form a new table. So they sit at that table with probability proportional to alpha, but the proportional constant is 1 over alpha, and so that was easy. What is the probability of the second person in this particular configuration sitting at the same table as the first person? Great. 1 over 1 plus alpha. Because there is one table with one person sitting at it. There's always the possibility of a new table, and the second person has decided to share the table with the first person. What's the probability of the third person sitting where they are in this configuration? Alpha over alpha plus 2. So again, there are 2 people so far in the restaurant. Alpha represents the probability of the new table, and 3 formed a new table here. And we can keep doing this. We can say, oh, the 4th person formed a new table, so it's alpha over alpha plus the number of people in the restaurant so far. The 5th person sits at a table that already had one person at it, so it's 1 over alpha plus 4. The 6th person sits at a table that already had 2 people at it, so it's 2 over alpha plus 5, and so on. And in fact, we can write a general probability. A probability for capital N customers, where we say there are kn tables, and n sub k people are sitting at table k. So suppose we're going to write this general probability. Can anybody tell me what the denominator of this probability is going to be?
Yeah, alpha times alpha plus 1 up to alpha n minus 1.
Great. So the denominator, as was observed, is alpha times alpha plus 1 times alpha plus 2, all the way up to alpha plus n minus 1. And so we can see that this happened up here. We started with alpha, because the first person, their only option is to form a new table that happens with probability alpha. We divide by alpha. The next person has the option of forming a new table or sitting with an existing person, and there's one person so far. And we keep doing this, and in every step we say that a person has the probability or the option to form a new table or sit at a table with any of the existing people, and the number of existing people for the nth person is n minus 1. So that's the denominator. Okay, so there are two possibilities in the numerator. There's the possibility where we form new tables, and there's the possibility where we join existing tables. So can anybody tell me what the factor in the numerator is for all of the new tables that were formed? I heard a lot of things, so can I get maybe a hand so I can draw on somebody in particular? Great.
Alpha is equal to kn or k minus 1. I don't know if you come the first one.
Sorry, can you repeat?
Alpha is equal to k bkn.
Yeah.
Maybe bkn minus 1. I don't know.
Great. Well, okay, so the two proposals were alpha to the big Kn or alpha to the big Kn minus 1. Well, we can double check up here, right? So here there were 3 tables formed, and there were 3 alphas. And in general, you can say there's 1 alpha for every table that's formed, and so alpha to the Kn. And actually, it's not totally unreasonable to say alpha to the Kn or alpha to the Kn minus 1, because one of these alphas you could just cancel with this one. But since we haven't, it'll be alpha to the Kn. Okay, so there's this final probability that represents everybody who joins a table that already exists. And so let's look at this again in particular for, say, this first table. So what happened at the first table? Well, first we formed it. Then one person joined a second person joined it. Then a third person joined it. And then a fourth person joined it. So what do we think is going to be the probability that represents people joining existing tables?
Product of nk minus 1 factorials.
Exactly. Product of nk minus 1 factorials. So we have a product over all of the tables, 1 to the number of tables. Then we have the number of people sitting at the table minus 1 factorial. And the reason it's minus 1 is because when I join a table, I have to look at everybody who's already sitting there, and when I join the table, that increases the count by 1. So the nk includes, this nk here includes the last person who joined the table, and when they made the decision, only nk minus 1 people were sitting there. Okay, so this is the probability of n customers sitting at kn tables with nk people at table k, and I'm just going to slightly change the notation on this and say that, I'll say that there are number C people sitting at table C. So I don't have to have this sort of K subscript sitting around. But this is just exactly the same notation. And what's nice about this is now I'm just able to do a product over the tables in the partition. And this is my probability of the partition. Okay, so one thing that's interesting to note at this point is that the probability does not depend on the customer order. If I happen to see the customers in a different order, it wouldn't change the number of people sitting at a table. And so therefore we have exchangeability, that the order of the customers doesn't matter. So in particular, an example of this would be, okay, so this is the partition that we actually see up above. 1, 2, 7, and 8 are sitting at a table. 3, 5, and 6 are sitting at a table. 4 is sitting at a table. And if I just permute all of those indices, if I give everybody a different label to have a different order, I come up with a different partition, but because this partition has 4 people sitting at this table, 3 at this, and 1 at this, it has the same probability. this useful? Why do we care about exchangeability? Well, there are a lot of reasons we care about exchangeability. We saw DiFinetti's theorem and everything in the beginning. But for the purposes of inference, what's going to be nice is that we're going to be able to treat any customer like the last customer. And so if you recall, this is your Gibbs sampling, which you reviewed over the break or definitely are already familiar with. The nice thing about Gibbs sampling is, or the way that Gibbs sampling works, is we take out one variable at a time and condition on all of the other variables. And so this is going to let us do some sort of Gibbs sampling type step. But let's forget about Gibbs sampling just for the moment and just notice what would happen if we took out one data point. So for instance, we might consider we have exactly the partition that we had before, and we take out 5. Like 5 left the restaurant, or he left his table because he had to go to the bathroom, so everybody else is still sitting at their tables, and then he comes back to the tables, and he does the usual Chinese restaurant set of steps. So here, what I mean by this notation, this pi n minus n, is that I'm taking out this customer from the restaurant. And so you can see here, I had pi 8 over here, 5 was in this table, and now I've taken 5 out of that table. And so the nice thing about pretending that that any data point n is the last customer is we know the probability of them joining tables when that customer comes back. So in particular, if we have, if we want to look at the probability of this clustering, given everybody else's belonging at tables except for one data point, say 5, in the example, but it could be any data point, little n, then we know there are 2 possibilities, right? They either join a new table, or they join an existing cluster. They join an existing table. And we know what these probabilities are because we know the Chinese restaurant probabilities. In particular, they join an existing cluster with probability proportional to the number of people who are sitting there, not including little n. So that's why we have this n minus 1. And they join a new cluster with probability proportional to alpha. So this is just exactly the Chinese restaurant process probabilities, only now we're saying that we're taking out any one little data point. No any questions up to here? Yeah?
Could you justify that this sums to 1? Because if I sum all the sizes of clusters, I get big M.
No, so here if I sum all the sizes of clusters, I get big n minus 1 because I'm not including little n. Yeah, so it definitely has to be a probability distribution. I agree with that. Yeah, I mean, I'm being a little bit fuzzy with this number C notation. But right here what I mean is the number of data points sitting at the cluster when I've taken out little n. Okay, so let me do a little bit more of a Gibbs sampling review. So the idea of Gibbs sampling is that we have some target distribution. We have some distribution over variables, let's call them v1, v2, and v3 here, but they could be any variables. And for some reason, we actually can't calculate that distribution. So this comes up all the time in Bayesian statistics because we're interested in the posterior. The posterior is proportional to the prior times the likelihood, but therefore we only know it up to a proportionality constant. And actually finding that proportionality constant is very difficult. Integration in general can be quite difficult. We'd rather not do it. And so we'd like to consider ways that we can approximate this target distribution. And the idea of Gibbs sampling is that we approximate this target distribution. We try to get something like samples from it. We try to approximate it with an empirical distribution. Now we can't do that exactly either, and so we're going to form a Markov chain that kind of looks like samples from that distribution. In particular, we'll initialize our Markov chain to some values. Good initializations are important in general, but it's hard to say what's a good initialization at this level of generality. And then we go through steps T, where we sample each variable conditional on the values of the other. So we sample v1 conditional on the values of v2 and v3, we sample v2 conditional on the values of v1 and v3, and so on. Now Gibbs sampling is definitely not the only way that you can learn and do inference in a Dirichlet process mixture model. In fact, there are many other great ways, there are many other good sampling ways, there are a lot of awesome variational inference ways. This is just a particular way that you could do inference. So I encourage you to check out all of those other ways. I'll mention some at the end, but I do want to go through this particular example. Okay, so before we build up our mixture model, let me just remind you of the generative model. And the generative model is just a little bit different here now because we're generating from a CRP. And so in particular, to generate our data, the first thing that we do is we generate our partition from the Chinese restaurant process. So we draw n data points, and we have this concentration parameter alpha. It's the same concentration parameter from the GEM. So we generated our tables. That's what essentially happened here. Now, for every table, we draw a mean. So the cluster mean. This is just like we did before. Before, when we had the GEM, we drew a cluster mean for every single one of the countable infinity of the possible clusters that we could have. And here we're just drawing them for every table, and that's kind of nice because we know that this is finite. So everything is already very finite. Everything that we're discussing here is something that you can absolutely do, and there's nothing being hidden under the rug. Okay, so we generate these means. So say there were 3, here they are. And now for every table, we look at all of the data points assigned to that table, all the people sitting at that table, and we draw their actual value, the actual observed xn, IID around that cluster center. And so that's what's happening here. We take the cluster centers, and we draw the x's IID around them. Now, again, in general, you wouldn't necessarily know these covariances, especially this one, so you might want to put some sort of prior on it. I'm not doing that here just for convenience of explanation, but that could absolutely be part of your cluster-specific parameters. And we want a posterior distribution. Now, what I'm going to do is I'm going to tell you what the Gibbs sampling steps look like. We're going to see that they look reasonable. And I'm going to leave it as an exercise for you to derive, and I think that that's absolutely something that you can do at this point. But in the interest of time, we're just going to look at that. Okay, so by the way, in general, your posterior, the things that are latent here, the latent parameters, are the assignments of data points to clusters and the cluster centers. You might be interested in both of them. You might just be interested in the assignments of data points to clusters. And so here I'm going to show you a sampler just for the assignments of data points to clusters. You could either derive your own sampler for generating both, or you could add on to this sampler to get the means. You can do whatever you want. This one just happens to be for the assignments of data points to clusters, given the observed data points, given these x's. Okay, so the Gibbs sampler is going to be, we go through each latent assignment of data points to clusters, conditional on all of the other assignments and on the observed data, and we say, what's the probability distribution of that? So that's what this is. What is the distribution, essentially, of the nth data point, which cluster it belongs to, given the cluster belongings of all the other data points and the data points themselves. So this x really just represents x1 to xn. I've just gotten rid of the subscript. Okay, well, there should, again, be 2 choices, right? You either join an existing table, or you start a new table. And we're going to see that the update steps look almost exactly the same as for the Chinese restaurant process, except there's this new part that incorporates the data likelihood. So this looks just like our generative model. This is just from the Chinese restaurant process itself. Think of this as like the prior. And what we're seeing here is the data likelihood. What is the probability of this new nth data point, conditional on it belonging to this cluster, given all the other data points in the cluster? So for instance, let's say I'm conditioning on this cluster. If my data point's here, that's going to be a really high probability. If my data point's here, it's going to be a really low probability. Same thing here. We have the probability of joining a new cluster, starting a new cluster. And then this is basically this data point where nothing's in the cluster, or this is the exact same formula as this where nothing's in the cluster, so we're sort of conditioning on nothing, or C is empty. And so this essentially just comes from the prior. It's saying, well, what's the probability of this data point being out there? And so the way that we're going to run our Gibbs sampler, and I'm going to show a demo in just a moment, is that we're going to cycle through each of the data points one at a time and sample its indicator variable. Just for completeness, I will tell you what these formulas are in the in this particular Gaussian mixture case. So again, a lot of these ideas are not specific to the Gaussian mixture, but in case you wanted to go out and try your own Gaussian mixture, I'll tell you what they are, and we'll get a little bit of intuition about what's going on here. Okay, so the inverse of the covariance matrix is often called the precision. So what we're doing here is we're taking the prior precision and adding to it the number of data points in the cluster times the likelihood precision. So if we were in one dimension, and this was just the variance, as the number of data points in the cluster grows, this whole thing would become very large, and therefore this sigma tilde, or the variance, would go to 0. So if we were in one dimension, that is what would happen. And so we would get this thing going to 0. Okay, now what's going on down here? Well, what we have is essentially a weighted average. We're weighting the prior mean by the prior precision, and we're weighting the data points by the likelihood precision. And then we're dividing it all by, again, in one dimension, this would be division, by this precision. So now again, let's imagine in one dimension that the number of data points is getting extremely large. Then this is going to kind of look like number of data points times the precision. These will kind of cancel, and we'll basically get a mean of the data points. So as the number of data points in the cluster gets very large, this is going to look like empirical mean of the cluster, 0 plus the likelihood covariance of the cluster. And so what that's saying is that for a new data point in this cluster, we expect it to just be distributed around the empirical mean with the likelihood covariance. Yeah?
Sigma tilde is now equals to 0, then the L tilde would be also kind of 0, no?
Yeah, so the key thing here is that these are sort of going to be the things that are behaving the same. So what we're going to get is something like this sum divided by this number. And that's how we're going to get the empirical mean. The prior stuff is going to go away as long as the number of data points is getting very large. But yeah, I agree. They're both going to grow in basically the same way. Yeah?
We need a slightly abusive hypothesis that sigma is the same for all clusters. So how do you generalize both formula if it's a sigma c? You just replace sigma by sigma c.
So is the question, what do you do if the sigma is not the same for all clusters? Yeah, so if sigma is not the same for all clusters, then you also are going to want a prior on the sigma. You want to learn that as well. And so it gets a little bit more complicated. It's just more equations than I wanted to put on a slide, but you can definitely do it. And you have to start thinking then about what are reasonable priors to put on sigma. Inverse Wishart is easy, but it has a lot of problems, so it gets more complicated. Okay, I'd like to show a demo. Oh, I'll just note before I do this that again, this is all quite a bit more general. This does not have to be just for the means. This could be for a more general distribution, including something that incorporates the covariances or something for topic modeling. But let's just go back to the one with the means and do the demo. Okay. So let me talk about what's happening here first. So what I've done is I've randomly generated a bunch of data points. I've randomly generated them. I chose, in my infinite wisdom, to put them four clusters centered at -3, and sort of every combination of plus or minus 3. And the data are generated around them. And so that's what we have here. The points that you were seeing are just data in the two-dimensional plane. And now what we'd like to do is we'd like to recover the clusters. And we're going to use Gibbs sampling. And so the first thing that we have to do in Gibbs sampling is initialize our sampling. Well, I don't know what the clusters are, so I have to initialize it somehow. And so something that I might do to express my lack of knowledge is just say that everything's in the same cluster. So I randomly drew some color that now all of these clusters share, and that random color, which is shared by everything, represents that everything is in the same cluster. And now the way the Gibbs sampling is going to work is we're going to go to each data point in turn, and the data point that we're currently on is going to have this big black X over it. And we're going to sample its cluster belonging. Which cluster does it belong to? Which table of the Chinese restaurant process is it going to join? Well, I initialized everything in the same table of the Chinese restaurant process, so there's only one existing table. It's the table that everything else belongs to. So there are two choices for this data point. It can either belong to that one giant existing table that everybody belongs to, or it can join a new table, which also has a random color. And so here we see the Gibbs sampling probabilities for those tables. There's the one giant table that everybody belongs to, and the new table with the new random color. And in particular, one of the reasons that I take the existing data point and mark it off as black is that it has no cluster belonging at this point. We're going to draw its cluster belonging from every other data point's cluster belonging, conditional on all of them, but effectively, we've forgotten whatever cluster belonging it had before. Okay, does anybody have any questions about this so far? Yeah?
Could you have started with no data points assigned to anything?
So you can't start with no data points assigned to anything. You have to have some initialization of cluster belonging, but we'll explore an alternative initialization in a moment. And then I encourage you to think yourself about better initializations because both of these initializations are not great. Yes?
So I'm confused. What is division of the 0, 1 line comes from?
Great, okay, the question is, where does this division of the 0, 1 line come from? Okay, so remember, let me just break out of this for the moment. Okay, so remember in our Gibbs sampler, we're going to sample the assignment of each data point to clusters conditional on the assignments of all the other data points. And that's going to leave us with a probability distribution. These are the probabilities of joining existing clusters, and this is the probability of a new cluster.
So my question is like it's alpha set fixed.
Oh yeah, here alpha is fixed. Yeah. And a great question would be, you know, why choose that alpha? And in reality, as we've discussed a few times now, you should probably be learning alpha as well. But for now, let's just presume that alpha is fixed. So if alpha is fixed, then I can just calculate these amounts. And actually, even if you were learning alpha, if you were doing something like a Gibbs sampler, it would be fixed in this stage, you would condition on alpha, and then when you get to the alpha stage, you would condition on everything else. But for now, let's suppose that we're doing this. Okay, so now we have this probability for the one existing cluster, because there's only one cluster right now. And we have this probability for joining a new cluster. So there are only two probabilities that exist at this point in time. And so these are the two probabilities we see. So there's the random color for all the cluster assignments. That's this one giant probability. You can tell because it's the same color as the cluster data points. And then there's the join a new table in the Chinese restaurant process probability, which is over here. And it's not surprising that join a new table is kind of small in terms of probabilities because, well, you know, all of the nearby data points to this point have the same cluster assignment as it does, and so maybe it's not too crazy to say in the same cluster. Okay, so what I'm going to do now is, so we're on Gibbs sampling iteration 1, data point 1, and the first thing we're going to do is actually run the Gibbs sampler. We're going to say, okay, for this data point, let's draw its cluster belonging. And that's what I've done here with this uniform random draw. So this red triangle, as we've seen before, is a uniform random draw, and we can see that it happens to have fallen into stay in the same cluster as everyone else. And so that's what we've chosen for this data point. So now we went to a new data point over here. It happens to be our second data point. These data points are ordered just in the order that they were generated. And again, it's the same thing. There's only one cluster that exists so far. I've also just highlighted that over here, the number of clusters, if you don't include the current data point, because you shouldn't, because it doesn't have any belonging, is 1. Every data point is assigned to the same cluster right now. And there's always the possibility of joining a new table, and it happens to be that that possibility is just extremely small in probability. Yes?
Go back one slide. You have the probability of belonging to this cluster, which looks like distance measure. This is why in this case, for that point, it looks like it's very useful. How do you compute that probability?
So is the question, how do we compute the probabilities down here?
No, so if you go back one slide, on the branch, we have the part that comes from the Chinese restaurant process, and we have another probability.
Great. So let me,
So it's the part of probability of these, the second part of the equation.
yeah, so this is the probability of joining a new cluster, and that was the thing we saw in the second color.
But there is a part that comes from the Chinese restaurant process, and there is a probability that belongs to the
Yes, yeah, so the Chinese restaurant probability and the likelihood probability, yeah.
And the second part, how do you compute that?
Oh, this is just the prior, essentially. So you can think of it as computing this, where C is empty. So when you put it in C equals empty here, this number is 0, this sum is 0, and it just becomes the prior.
But in this case, so for example, which you randomly pick to belong to a new table, it depends on the alpha
Yes,
and the second part of the probability.
yes,
Everything else is known.
yes.
And what you pick at the bottom is that probability.
Right, so what we're doing is at the bottom we're plotting these probabilities. They're going to be probabilities that sum up to 1. And then the way that we choose which cluster to join is we make that uniform random draw. And that picks from these probabilities with those probabilities. Yeah. Okay, so at this point we've done 2 data points. This one, the probability of joining a new cluster was just incredibly small, so small that we can't even see it on this plot. And we drew a uniform random variable, and no surprise, it is in the same cluster. And so now let's go to the 3rd data point, stays in the same cluster. So you might not be able to see this. This uniform random draw just decides to stay in the same cluster. Almost something interesting happened. Same cluster, same cluster. Whoa! Okay, so this data point, we calculated its probabilities in the Chinese restaurant process. Here's the probability of staying in the same cluster as everybody else, and here's the giant probability of forming a new cluster, and in fact, it does form a new cluster. And so when we go forward, we see that now this data point belongs to a new cluster. There's a couple of questions. Let's take them back first. Okay, so the question is, what is the intuition of this data point having a higher likelihood to join a new cluster? And my guess would be that, so in these clusters, we have quite a few more data points that are surrounding each of the data points, whereas here, there aren't quite as many, and so maybe there's more sort of likelihood that it could just be forming something new. That's my guess. Yeah.
Probability that the data point is added to the new table changes because the prior solution the data point changes.
So the probability again is this combination of the Chinese restaurant process and this data likelihood. And so the data likelihood is essentially saying, how likely is it that this data point came from the distribution that I see? And so if you think about it, so there's all of these points right now are in the same cluster, and that cluster has an empirical mean, and it's probably somewhere kind of over here right now, because there's so many data points over here. And so this data point down here is quite far from that empirical mean, and so it seems less likely to be a part of that cluster. Okay, so keep going. Oh, I Should have went a little bit too fast, but okay, great. So this is a nice illustration. So now we see that there are these two tables, and technically speaking, for every draw we make at this point, there are two table options because we're two different clusters that are out on the board somewhere. And now this is the new cluster, the new table in the Chinese restaurant process. And so we just keep running this, and you can see that a new table at some point was actually formed down here. Yes?
When you assign everything to the first cluster, you also pick the cluster mean, I guess.
So I didn't, actually. So when I assigned everything to the first cluster, I did not pick a cluster mean. And so we go back and look at the sampler. It's essentially using an empirical cluster mean here, and that's how it's getting information about the cluster mean, but at no point am I actually sampling the cluster mean or picking the cluster mean. And that's actually one of the benefits of this kind of sampler, or one of the potential benefits over something that actually includes the cluster mean, is that we don't have to sample it. We can easily sort of move our data points around without that intermediate step. There are definitely other problems with this, though, and I'll talk about that as we go. Okay. Okay, so this keeps going. Now these data points that are sort of close to this cluster seem to have a high probability of joining that cluster, probably because their empirical mean is quite close to that data point. We see now that there's one cluster down here that's different from this cluster. So at this point, we actually do have 4 total clusters. And this keeps going. And rather than go through all 100 data points to finish the Gibbs iteration, I'm just going to skip ahead and look at as though we had done the full Gibbs iteration. And this is what we have at the end of one Gibbs iteration. So one Gibbs iteration, that is, we visited every one of the 100 data points. There's 100 data points on the board here. And we said, let's sample its cluster belonging conditional on all of the other cluster belongings. And we see that we're doing pretty well, actually, at this point. You know, we've almost got all the data points in this area into one cluster. We've almost got all the data points in this area into one cluster, and same thing over here. And so, in fact, let's go one more Gibbs iteration through all the data points. And we've got all of the data points pretty much in the clusters that we would expect. Yes?
So, I'm confused. Why it is not evaluate another cluster, for example, right upper corner, because then create like 2 cluster distribution within this one cluster.
So is the question, why didn't it try to add a new cluster in this area? Well, my suspicion, and again, this is just intuition, is that, so if you look at the numbers of the data points in each of these groups, this one has the largest. And so somehow that giant cluster that we started with was closest to the empirical mean of this one. And so it eventually sort of just came to represent that one. Whereas all of these other ones needed a new cluster to really represent them all.
So why not? Why this? So I'm confused. But from time to time, you should have a chance to something like new cluster, like fifth cluster.
Oh yeah, okay, right. So the question is, why doesn't it from time to time sample a new cluster, a fifth cluster? It absolutely does. So there's, technically speaking, actually I can even kind of see it, the probability of the fifth cluster down here. It's just that these are such well-separated perfect clusters that it's extremely low probability. If you ran this for a really, really long time, you would eventually get some of these data points joining a fifth cluster. But because it's so low probability, it's unlikely that we would see that if we ran this for a little while just now. But that fifth cluster absolutely does exist, and it has a non-zero probability. Question back there?
If it appears once, then it doesn't disappear further.
Oh, so if a cluster is the question, if a cluster appears, is it always there forever after? No. And a way that you can get rid of a cluster is suppose it gets down to when it only has one data point. And now I sample the assignment of that data point, that cluster is gone. Because as soon as I sample this data point, its assignment is gone. And so now when I'm choosing this data point, even if it belonged to its own unique cluster before, I'm only choosing from the 4 existing clusters and a totally new cluster. And so that's how you can get rid of a cluster. Yeah?
Each iteration, you start from the end of the previous iteration, right?
Yeah, so each iteration, I go through all of the data points, and then I just go through all the data points again, and I haven't changed anything from right before. Yeah?
Could you have calculated the
in the start and shown that on the spot?
Yes, I absolutely could have calculated the empirical mean and shown that on this plot, and unfortunately I didn't, but I will make the code available to all, and you can plot that. And it sounds like a great idea. I like it a lot.
Isn't it that whether it separates a cluster largely dependent of our prior over the covariance?
Yes, yes, there are so many prior choices that go into this and that are so important to this. One is the covariance. I happen to have chosen the covariance really carefully beforehand that really agrees with the covariance of these actual clusters. If you really wanted to learn the covariance, you should put a prior on the covariance and learn that as well. Again, the reason that I did this is because I didn't want to put as much notation on the slides, but it's totally something that you can do. You can learn the covariance and put a prior on it. Something you should also be concerned about that absolutely influences this is, again, the choice of alpha. So if I had a really poor choice of alpha here, I might end up with tons of extra clusters that are not actually here. Because alpha will really force me to have, in the right direction, a really bad number of clusters. So again, something that you should actually be learning. Yeah.
We cannot be learning with putting a prior and doing the sampling step?
No, you can absolutely do that. All of these things you can put a prior on and add another sampling step. For alpha as well. Yeah. Yes?
So the final solution is then a solution after a predefined number of steps, or do you average the steps?
Right. So what do you do with this at the end? So typically the thing is you run a burn-in number of steps, and so until you've reached a point where things aren't changing anymore with your sampler, and then after that point, you say that the samples that you were getting are like samples from the empirical. And that might be actually after a few number of iterations, but then once you have these empirical samples, you can say things about probability. So for instance, if I had a point that was right here, it would probably occasionally get assigned to either one of these, and so over many, many iterations, I could say what's the probability of it being in this cluster versus this cluster by looking at the empirical average there. Same thing with the means of the clusters, this would be especially more informative if we had clusters that were kind of squished together or not as obvious. I could look at the means over many, many iterations and say, what's that distribution? Yeah?
So if alpha is so important and determines number of clusters, what's the advantage to having a fixed number of clusters and using that as a parameter and using Dirichlet, so not having this GEM?
Okay, so I believe the question is, why not use a fixed number of clusters and put a distribution over it if alpha is giving us all this trouble and headaches? Right, so the difference is that the prior and alpha are kind of doing the same thing, but the ultimate behavior is very different. So if I put a prior on the number of clusters, and I have a fixed number of clusters, and then all my data is generated from that, the fact is there is a fixed K. There's a fixed number of clusters in my data set, and eventually I will hit that K. And so this is like the moth experiment. I've got a bunch of moths in my room. I don't know how many there are, but I think that there's at most 8. And so I put my prior on the number of moths, and eventually, or the number of different types of moths, and eventually I just get to the limit. And no matter how many more moths come in, or how many moths have moth children, there's sort of only this limit on the number of types of moths. Whereas if I'm doing something like I'm modeling Wikipedia, then I don't want to eventually hit a number, or I might not want to eventually hit a number of topics. I might want that to always be growing, or species. I don't want to eventually hit 1,000 species. I want that to always be growing. And so if you have a prior on a finite number of clusters, you're saying that your data is generated from some finite number of clusters, you just don't know that finite number. In this case, we're saying that the data is generated from a number of clusters that is always growing, and we want to model that always growth. So it's a different type of model.
So if I use different alphas, I get a result of 10, 100, and 1,000 clusters. Is it easier to find which one is best compared to if I just use fixed number of clusters, 10, 100, and 1,000?
Right, well, so what alpha is telling you, though, is the rate of growth. And so if you really believe that your data is actually always generated from the same distribution, and it's just that that is the way that you are getting more growth, that you are actually sort of sampling, in some sense, the rarer things over time, the new topics that you didn't see before, then that's what alpha is telling you. If you have a prior and you change it over time, and you're saying, oh, we're going to let it get bigger and bigger and bigger, then you're essentially having a time series model. You're saying your data isn't stationary, that something different is happening in your first set of data points than in your second set of data points than in your third set of data points. So it comes down to, do you really think that your model is a stationary model and that's what's giving you the growth? Or do you really think that your model is a time series model and that's what's giving you the growth?
So back to using all the samples. I mentioned that it's possible that the cluster ID might change for two samples, even though maybe two IDs might correspond to roughly the same data points. So how do you combine these different samples?
So is the question that I might have a data point and as I sample more and more, the cluster ID occasionally changes?
Yes.
Right, and so what that does is over many iterations, it tells you the probability of that data point being in the different clusters. And so you take the fraction of the time that the data point is in one cluster, and that's an approximation to the probability, the posterior probability that the data point is in that cluster.
But how do you match cluster from one, gives something an iteration from two?
Oh, right, okay, so there's another issue here, which is the so-called label switching problem. So if you have clusters and you run this forever and you keep running this, it might be eventually that somehow this cluster, this label migrates like over here. And then how do you calculate the mean? You know, that's not going to give you a good idea of the mean because you'd be averaging things from over here with things from over here. This is a hard problem. It's one of the reasons that people actually don't like Markov chain Monte Carlo in a lot of ways, and one of the reasons that alternative methods like variational inference have been popular. So for a long time it was considered to be sort of a bug in variational inference that it tends to pick out a particular local extremum. But actually in this case, in the sense that, you know, there's this entirely equivalent clustering where I just reorder the cluster labels, and that's just another local extremum, well, picking out just one of those is better here, because then you just pick out one of the cluster labelings. And so that's a potential reason that you might like to instead use a variational inference algorithm instead of a clustering algorithm. It's a great point. Yeah.
What if you have very high dimensional data?
Yeah, so if you have very high dimensional data, then there are all kinds of other issues that you could potentially get into. One thing that's nice about Bayesian statistics in general and high dimensional data is that you have this regularization effect that's happening with the prior. And so that is a reason to like the idea of using priors. That's not specific to this, or to the non-parametric side, that's just specific to the Bayesian side.
How much can the initial cluster allocation affect the conversions?
Great. I would like to answer your question with another demo. Okay, so the question was, how much can the cluster initialization affect the ultimate convergence? And so let's try this out. So here's another cluster initialization. So the cluster initialization that I previously did was I said, hey, let's assign every data point to the same cluster, because I don't know, how to assign data points to clusters. And so that seems like it expresses my total lack of knowledge. Another way that I could express a lack of knowledge is I could say every data point belongs to a different cluster. So again, what I've done is, I've randomly assigned a color to every cluster. Because there are 99 points except for the one that I give sampling, there are 99 clusters on the board right now. And so when I run my Chinese restaurant process, or my give sampler, then I will sample from 100 different probabilities, because it's 99 plus the one for the new table. And so there are, technically speaking, 100 different intervals down here. And I'm just choosing a particular one that seems almost meaningless at this point, because everything is a different cluster. And so I can keep running this like I did before, and it's a little bit harder to see what's going on because there are just so many clusters. And so maybe let's just skip ahead to the next Gibbs iteration. So I'm going to skip ahead to after we've sampled all 100 data points. Okay, well remember when we initialized everything to the same data point, then by this point things were looking pretty good. Now when we've initialized everything to a different data point, well, almost miraculously, a lot of this seems to be in the same cluster, although this is a different cluster. But I mean, the rest of these are just still a mess. There's tons of different clusters. In fact, we still have 38 total clusters. Okay, so we can go ahead another Gibbs iteration. We can go ahead another Gibbs iteration. I'm just going to go ahead 5 Gibbs iterations. Okay, wow, we're 10 Gibbs iterations in, and it still hasn't really totally mixed. This is pretty good. This is pretty good. There's 2 clusters here. And they're both pretty good. If you're a data point that's over here, let me see if I can get to a data point that's over there. Yeah, there we go. Both clusters look pretty reasonable. I mean, the mean of the one cluster is pretty close to me as a data point. The mean of the other cluster is pretty close to me as a data point. How am I going to choose between them? And this is a big problem. This illustrates a big problem with Gibbs sampling in general. That you're only able to make these small incremental moves. You can only change the assignment of one data point at a time. What you really want to do is make this big move and say, oh my gosh, these are just the same cluster. Let's combine them. But you don't have that option with this particular sampling algorithm. And that's something vaguely similar is going on here too, but on a lesser scale. And so we can go forward another 5 iterations, and it looks like finally we've gotten our 4 clusters. And so that's not to say that, you know, initializing everything to the same data point or to the same cluster is necessarily better than initializing everything to different clusters, but that initialization really does matter. That it really does make quite a difference. And perhaps there's something faster or more sort of meaningful that you could do in this case, something that takes advantage of your knowledge of the problem, even something like initializing with like a k-means algorithm. And it's also, again, I want to emphasize this point about Gibbs sampling, that you're making these small incremental moves, and you might have a really hard time actually getting around your space that way. Okay, are there any other questions about this demo?
Is there maybe a way to, I mean, if we don't know which one of the initialization is best, can we try to run the 2 algorithms parallelly? And each time we sample the point, we use them for 2 algorithms, and at the end we have some sort of distortion measure to know which one is the best?
Well, so one thing you could do. Well, one thing you could do is you can run multiple Gibbs iterations, so you can or multiple initializations, run your iterations, and then you can do various checks to see how well you're doing. So you can see, you know, are you getting to a better local maximum in the space in terms of like likelihood or posterior probability? Are you getting better performance in terms of mixing, things like that? So that's absolutely something that you can track.
Can you sort of integrate some iterations of k-means in between?
So that's tough. So the proposal was, can you interleave some iterations of k-means with this? So the nice thing about Gibbs sampling is that we have all these nice guarantees, these theoretical guarantees that say, oh, you know, at the end of the day, if I run my sampler, I'm actually, you know, in the limit of infinite time, but at least in some limit, I'm going to actually be getting samples, like empirical samples from my make. As soon as I stop doing something that has these Markov chain Monte Carlo guarantees, I get away from that. Now, there's some really new, interesting research, and a paper by Gorham and Mackey that shows ways to evaluate your sampler, even if you get away from these sort of, you know, guaranteed Markov chain Monte Carlo limits. But that work is very, very new. And pretty exciting, actually. Yeah, exactly, using Stein's method. Okay, so all this code will be online for you to play with. And I can guarantee you that you can come up with better inference algorithms than the one that I just showed you. This is just to give you a sense of what's out there. You can also come up with worse ones, but don't do that. Okay, so let me just go over some exercises at this point. So code your own simulator. Don't necessarily use my code your own. You have the information in these slides and you can derive them, and so try that out. In particular, make sure that you can derive these sort of likelihood terms explicitly for yourself, and that's sort of just a parametric Bayesian derivation. What if you want to sample the cluster-specific parameters, like the means as well? You might want to try that out. And there are many other samplers that are out there. So NEAL 2000 is a good starting point, but it's certainly not the ending point. It collects a certain amount of knowledge that existed in 2000, and then there's quite a few beyond that. A really neat idea, which is just kind of beautiful, is slice sampling. And so it turns out that we didn't need to go to the Chinese restaurant process to get away from infinities. That we could actually use an idea like the one that we did with the GEM, where we said, we'll just generate as many beta sticks as we need until we get to that uniform random variable. Turns out we can use an idea like that for inference. And so that's what happens in slice sampling. And it's quite a beautiful, powerful idea. We already mentioned why you might prefer variational inference, and so there's a number of papers on variational inference, not just for the Dirichlet process mixture model, but for other models in general, and so that's definitely worth checking out. Variational inference, on the other hand, has some problems that sampling doesn't. So for instance, if you're really interested in things like uncertainties and really accurate, actually capturing the posterior distribution, you don't get the same guarantees with traditional ways of using variational inference as you do with Markov-Chain Monte Carlo, although there's been some research about getting beyond that. And then if you're interested in getting into a little bit more theory, as well as an overview of everything that we've talked about here, you might check out this last paper. Okay, and with that, what I'd like to do is just give you a really brief overview of some of the other ideas in Bayesian nonparametrics. So this list will by no means be exhaustive. It's just going to be sort of a taste of what's out there. And I will just, sort of tell you about the path that starts with Dirichlet processes and Chinese restaurant processes and leads into sort of a whole wide world. Okay, so here are some of the other ideas that we'll talk about. So one is, we've talked about clustering this whole time. Maybe I'm clustering documents. Maybe, I've just been hired by the New York Times and they want me to take their documents and come up with really natural clusters. And lo and behold, I clustered my documents and it turned out that some of them were about the arts and some of them were about economics and some of them were about sports and health and whatever. And I found this in a totally unsupervised way. I didn't just use their existing labels. Okay, but in the course of clustering these documents from the New York Times, I was looking at an old review of the movie Moneyball, and if you recall, Moneyball was a movie, so it's kind of about the arts, and it was a movie about trading baseball players, so it's kind of about sports, and it's about trading and making money, and so it's kind of about economics. And so it doesn't really fit into just one cluster, it actually fits into maybe multiple clusters. And so in this case, instead of a latent clustering, I might have what's called a latent feature allocation. And just as there is a Chinese restaurant process for clustering, the culinary metaphor in this case is the Indian buffet process. So in the Chinese restaurant process, I come in, I sit at a table, and I eat a dish, and that dish is sort of my parameter, and that parameter represents that I'm actually a document about the arts, or I'm actually a document about economics. In the Indian buffet process, I come up to the buffet, and I take a few dishes. In fact, I can take any finite number of dishes in a particularly specified way. And those dishes represent, again, the features now that I belong to instead of clusters. So I could be about arts and economics and sports. Those could be the dishes that I pick up in my Indian buffet. Just as the Chinese restaurant process is the marginal of the Dirichlet process, or the GEM, together with the categorical likelihood, so is the Indian buffet process the marginal of something called the beta process, together with the Bernoulli likelihood. So the Indian buffet process was introduced by Griffiths and Garamani. Fun fact, the beta process was discovered independently by Hewart in the survival analysis literature in 1990. Maybe that's not so surprising because actually the Chinese restaurant process, or the Blackwell-McQueen-Ern scheme, as it was essentially originally called, was discovered independently from the Dirichlet process, which was discovered by sort of essentially Ferguson in 73. Even the stick breaking was discovered independently. So. And then there's been a lot of development since then in terms of these feature allocation models, these assignment of data points to multiple groups. There are a lot of other structures that we might want to model. So genealogies come up a lot in genetics. We want to talk about genealogical processes, we want to talk about trees, we talk about things like that. And so one of the sort of foundational ideas in this area is the Kingman coalescent. Introduced by Kingman in 1982. You might not want to just have strictly a tree, you might want to have something that can both fragment like a tree does, but also coagulate back together. It turns out there are biological reasons to like that, and so these processes have been introduced as well. And you might want a tree that couples with sort of like times of fragmentation and sort of distances along the tree, and so you can get that with a Dirichlet diffusion tree. Okay, so something that I asked you to think about, and I understand that you didn't have too much time to think about it, but let's think about it together now, is the rate of growth that's encoded in the Chinese restaurant process. So we said, I told you, and I would think it would be great if you went and derived this for yourself, that asymptotically, the number of clusters occupied by n data points in the Chinese restaurant process, this is just a fact of the Chinese restaurant process, or the GEM with categorical likelihood, is that it grows as alpha log n. Okay, so when I use this squiggle here, so previously we've been using it for, this random variable is simulated according to this distribution. But here, this isn't a distribution. This is just a discrete, this is just a fixed function. And so when this is just a fixed function, this notation means that this over this goes to 1 as n goes to infinity. And so what we're saying here is that the number of tables in the Chinese restaurant process grows logarithmically, and linearly in alpha, but logarithmically with the number of data points. And it turns out that that's actually not realistic in a variety of scenarios. So for instance, there's this law that's been observed that, so let's say we're talking about documents. So in documents, you could talk about tokens, which are the individual words in the sense of if I have something like the cat and the other cat, so that would have the cat and the other cat 6 tokens. But it would have 4 types, the cat and the other, cat. Okay, so I think that's 4 types. But 4 unique words and 6 actual words. And so what's been observed is that the number of types actually grows as a power law of the number of tokens. It grows proportionally as the number of tokens to a power. So something more like n to the alpha instead of alpha log n. Or n to like a new thing called sigma. And in fact, people even know kind of what sigma is, that it happens to be between a certain range, that happens in 0, 1. And so this is an observed law, and in fact, there are a lot of other areas, a lot of other applications where people observe power laws all the time. Power laws are somehow this fundamental kind of growth rate that is just very, very commonly observed. And so what do we do if we actually want a power law, which seems to be more realistic than the Chinese restaurant process? Well, it turns out there's a thing called the Pitman-Ure process. And it's very much like the Chinese restaurant process. It has a stick-breaking representation, it has a Chinese restaurant process marginal representation, it has all of these nice things that we use this whole time, but it also has power law behavior. So the number of clusters for the Pitman-Ure process actually grows as, this happens to be some random variable, but it doesn't depend on n, as essentially n to some sigma, or sigma between 0 and 1. By the way, this turns out to be related to Zipf's law as well, that if you rank the frequencies of many things, that you will often find that those decrease with the power law. And there's some interesting work by Gidding et al. On doing this in the clustering case, but you can also look at this in feature allocations and lots of other different applications. Okay, hierarchies. One of the reasons that people like Bayesian statistics so much is that you can use hierarchies. You can share strength across different types of data. So for instance, maybe I have data on different hospitals that are all across the country, and I want to find out something like a survival rate for a particular rare illness. And it turns out there are some hospitals that have a lot of people with that illness, and so I can say something really meaningful about the survival rate, but some hospitals don't have much data. And so if I have a shared prior across all those hospitals, I can sort of get a little bit of information. I can share strength for one of the hospitals by applying information from the other hospitals via that shared prior. And we can do the same thing with all of the tools that we've created, the Dirichlet process, the Chinese restaurant process, the beta process, even though we haven't talked about what that is. These are just distributions that we can now put into our Bayesian toolbox to make ever more complicated models. And so the hierarchical Dirichlet process in particular is very useful if we have something like, say, I have all of these books over here, I have like maybe the New York Times over here, and I have some local newspaper over here, and maybe I have a newspaper that focuses specifically on science over here. And I think that there's somehow a set of topics that newspapers in general share, but I think that each of these newspapers individually picks out just a few of those topics. And so maybe I want this underlying Dirichlet process that says, here's all the topics in general in the world, and then I'll have a next level of Dirichlet process that encodes each of the individual different types of newspapers. And so it's a hierarchical Dirichlet process. And because, of course, we need to have some type of culinary metaphor, because that's the cool thing to do, the culinary metaphor here is the Chinese restaurant franchise. So each in my example, we were talking about sort of newspapers. Each set of newspapers, each set of documents in a newspaper is a restaurant of its own, and then people walk into that restaurant. Those would be the documents within, that newspaper, and they get dishes, and the dishes are somehow shared from this, repository of topics, as it were. But people definitely love their culinary metaphors. Okay, and there's similarly a hierarchical beta process, and you can play this kind of game in general. Okay, so fun fact: here is a way that you could generate an exchangeable cluster. It's very similar to what we've been talking about today. First, generate a partition of the unit interval. We know one way to do that, the GEM. We know another way to do that, a Dirichlet distribution. So this partition doesn't have to have a finite number of elements. It doesn't have to have an infinite number of elements. It could have either. It could have, both with some probability. And the partition sizes could all be random as well. And now I'm going to do exactly what I did earlier, and I'm going to say I'm going to generate one IID uniform random variable for each data point. And when two data points fall into the same interval, they belong to the same cluster. Now, what's not so surprising about this is that this generates an exchangeable clustering. I could interchange any two of those uniform random variables, and I haven't changed the distribution. But what is surprising, and Kingman showed in 1978, is that every exchangeable cluster, no matter what exchangeable cluster you come up with, must have a representation of this form. You can always find a Kingman paint box, this potentially random partition of the unit interval, such that I make these IID draws from it, and that gives me back the same distribution as my original clustering. So in general, deep affinity mixing measures aren't necessarily constructive, they aren't necessarily nice, but in some cases they are, and the Kingman paint box is one such case. Similarly, for this feature idea where I can belong to multiple groups simultaneously, there's a feature paint box. For things like graphs or network data, where we are looking at edges and connections of edges, I have the idea that we can exchange nodes and say, oh, if I exchange these two nodes, I think they're exchangeable, I don't think the distribution changes, and then it turns out there's a deep affinity mixing measure that's given by the oldest Hoover here. And there's a nice overview of different forms of exchangeability that's more recent in Orbans and Roy, and I'd like to again direct you to this Aldous manuscript that's also quite a nice overview. Despite being from 1983, it's still extremely relevant. So conjugacy, it turned out to be useful for us in a variety of ways. Just in conjugacy of normal distributions within clusters, it made our lives very easy. We were able to sort of do a lot of calculations very easily because of that. And these non-parametric processes are not only no exception, but conjugacy is almost sort of more important there. The conjugacy of the GEM with these categorical draws is what let us have this nice Chinese restaurant process. It's what let us have these nice abilities to update posteriors in finite time, despite essentially having this infinite dimensional processes. And in fact, you see that this kind of motif occurs again and again in the processes that we see. So the beta process together with the Bernoulli process gives you the Indian buffet. If you don't normalize in advance, it turns out the Dirichlet process is a normalized version of a gamma process. And so another way to get a Dirichlet process is to take a gamma process with a Poisson likelihood process and then normalize. And beta process, negative binomial processes, all of these processes occur in Bayesian nonparametrics. And the thing that I want to highlight here is that these are familiar conjugate exponential family pairs so long as you get rid of the word process. Beta Bernoulli, gamma Poisson, beta negative binomial, even Dirichlet multinomial. This just happens again and again. And these all are formed from Poisson point processes. And there was this question earlier about sort of how do Gaussian processes fit in together with this side of Bayesian nonparametrics. They're both sort of Bayesian nonparametrics. Well, if you're interested in this kind of thing, essentially they both boil down to Lévy processes. And the Gaussian processes are like the Brownian motion continuous side. And Dirichlet processes and beta processes and all of that are like the Poisson point process discrete side. So we're able to get these posteriors. There's a notion of exponential families, which again we see here in a notion of conjugacy in this case. Okay, so nonparametric Bayes. We saw that it was Bayesian statistics that is not parametric. We saw what that meant. In particular, we were using Bayesian statistics And we saw that in this particular example of the Dirichlet process, but certainly more generally than that, we were able to generate this infinity of parameters in a latent space, and that was what gave us a growing number of parameters, even though we had a stationary distribution in our data. That no matter how many topics we've seen in Wikipedia so far, there are always more topics in that latent infinity that we can draw on for our data in the future. And we saw, we didn't talk too much about these examples, but there are a number of examples, and certainly more than I could have fit on this slide. And so I'll encourage you to check those out. Thank you.
Yeah, so you mentioned here briefly that conjugacy is basically what makes Nonparametrics work. So you maybe comment on, do you think the machine learning community is too interested in conjugacy in their models and become out of hand, like construct models that
Great. So okay. So how reasonable? There's a couple of questions I think in here. So conjugacy seems to be what makes this work. How reasonable is conjugacy? So in some sense, it's definitely well known in the finite parametric case at this point that conjugacy isn't always reasonable. That there are a lot of cases where your prior really shouldn't be, in one particular parametric family form, and certainly not necessarily the conjugate one. I would say that a particular example of this would be something like an inverse Wishart prior for covariances. There's a lot of reasons to distrust those priors. And so in the parametric case, though, we have this interesting fact that, in general, especially if we're working with semi-low dimensional distributions, integration isn't that hard nowadays. I mean, I take that with a grain of salt, but somehow we kind of know what we're doing with integration. We have reasonable Markov chain Monte Carlo methods, we have reasonable variational methods, we can do pretty well. There's two things going on in the non-parametric case. So one is there's more of a computational imperative. As soon as we get to these sort of extremely high dimensional cases, this infinite dimensional case, having the ability to deal with conjugacy lets us just deal with it. It lets us do that computation in a way that I think used to be the case with parametric models and is no longer the case, or is less so the case. So we might be getting that way with non-parametric models. I mean, certainly, so there's some recent work on truncating models, on how well you're doing if you have some sort of finite dimensional approximation to your non-parametric model, which at first sounds crazy. Why would you do that? Why wouldn't you have just used your finite dimensional model to begin with? But the key difference is that you can change the truncation level as you get more data, and so you're still using the same stationary model for everything. But I would say that works in really early stages and still mostly focusing on a few sort of exponential family style models in Bayesian nonparametrics. And so it'll be interesting to see, it's tough in infinite dimensions because that thing that's around the corner, that infinite thing, if it could really be anything, that's almost sort of too much flexibility. So there has to be some kind of give and take. But yeah, I would say that the answer to that, if there is an answer, is in early stages.